and that is real numbers. When you discuss real numbers simply represent any point that can be located on a number line. Okay? With respect to a number line, the number 0 is referred to as the origin. Hey, it's a reference point. The 0 on a number line just tells you any number to the right is going to have what sign? And any number to the left is going to have a negative. And this extends all the way to infinity in the positive direction. It extends all the way to negative infinity as well. So infinity in the negative direction, and it'll have a negative symbol in front of it. Okay, so any point that you can plot on this number line represents real numbers. Now there's several subcategories of real numbers you need to be aware of and you've probably been exposed to. We'll start with the simplest of them, and that is natural numbers. Natural numbers will be designated with the letter N, and it'll have 2 bars on the slash of the N. Natural numbers simply mean all the counting numbers from 1 to infinity. So 1, 2, 3, 4, and so on. Okay. So the ... just means the pattern continues. So any counting number from 1 to infinity can be plotted on the number line, and it's referred to as a natural number. And now if you include the number 0 in that set, now you're looking at the set of all whole numbers. And so now within this box, the set of all numbers that are natural, including and in addition to that, the 0 represents all whole numbers. So does everybody see what I'm doing with the box here? Everything that's enclosed within is still classified under that outer label. And so 1, 2, 3, and 4 are also considered whole numbers. Okay, if you take all of these whole numbers and you want to include their opposites, so let's say you include -1, -2, -3, -4, and so on. Now you're looking at the set of all integers. And integers are represented with the letter Z. And once again, these include all the whole numbers, so 0, 1, 2, 3, and 4 are considered integers, as well as all the opposites of those, so -1, -2, -3, -4, and so on. Okay, so that's the set of all integers. Okay, if you want to, or first of all, what's missing from these two sets? Fractions and decimals. So if we want to include fractions and decimals, then we're dealing with rational numbers. Rational numbers are designated with the letter Q, again, often written with an extra line in one of the arcs. And a rational number represents the ratio of two integers. So a rational number is in the form P over Q, where both P and Q are integer values. Okay, so any number that can be represented as a fraction of two integers, or a quotient of two integers, is considered a rational number. So all of these numbers up here, all the integers, are included in those, as well as the following. We have terminating decimals. Okay, so any terminating decimal can be written as a fraction just by putting a power of 10 that represents its decimal place where it terminates. So 5.14 and can be written as 514 divided by 100. And so anything that actually terminates in the decimal form can be represented with a power of 10 in its denominator. And then the other one is repeating decimals. Has anybody here ever, in any of their previous math classes, gone through how to represent repeating decimals in rational form? Okay,
Is that where you put the bar? Yeah.
Oh, no.
Oh.
Okay, so that's one of the things that we'll be doing that is new to everybody. It's not written in the book. It's just something that we'll be doing outside. There are problem sets involving it, so it is something that you are expected to know. So the rational numbers, instead of just the integer values, you have fractions. So 1/2, -3/7. It would be examples. You have repeat or terminating decimals. The one I said, 5.14, -3.212. You also have repeating decimals. So if you had 1.33, and so the bar over the top simply represents that that pattern continues. So how many repeating digits are there in that number? Well, how many digits actually repeat one? One, right? So even though I have 2 digits under the bar, and usually it just tells you, or it just includes the numbers that are repeating. And so you might have a positive or a negative. And so here's an example where there's 2 digits repeating. You can also represent the repeating non-terminating decimals with a ... And if you have a ... again, it just means that the pattern continues. So here the repeating pattern is 5-1. So it's 2 digits that are repeating in that. And we'll talk a little bit more about that as we get to writing the rational form of those. Right. You also have a set of numbers that don't fall within this category of rational. And that set's called irrational numbers. And irrational numbers are just, again, the form that cannot be expressed as a fraction or a ratio of 2 integers. So the irrational numbers include square roots that don't reduce down to integer values. So things like square root of 2, square root of 3. And would square root of 4 be considered an irrational number? What's the value of the form square root of 4? 2. So what would be the most specific classification the square root of 4 could fall into? Natural. So square root of 4 would fall right here, right? And so if you were asked to identify or classify that number, square root of 4 would be a natural number, a whole number, an integer, and a rational. All of those classifications encircle that number 4, or that number root 4. And so root 5, you can have the negatives of these, so negative root 7. Also, irrational numbers represent the symbols that express irrational numbers, so pi and e are the main 2. We're probably not going to get to e this year. I think it's in maybe chapter 7 or so. Pi we've already talked about in the circles of geometry. Okay, so these are the main classifications here. All of these can be completely enclosed within the set of numbers that are referred to as real. So if you take this whole set here, all of these are classified as real numbers. And that's represented with an R with, again, that double bar push in it.